Please pause here.
That is what it sounded like when the person who built this telescope finally saw it work. On June 23, 2025, after nearly 30 years of work, humanity got its first real look through a brand new telescope, and the images stopped astronomers cold. What hit people so hard was the sheer amount of sky captured in a single frame. That is why many called it the biggest moment in astronomy since the James Webb Space Telescope's first images. The telescope behind it is the Vera C. Rubin Observatory on a mountaintop in Chile, carrying the largest digital camera ever built. And what makes it so remarkable is not just those first images, but everything behind them, and a discovery it made within its very first hours. Because as staggering as 10 million galaxies in one picture sounds, it turns out to be only the faintest beginning of what this telescope was built to do. If that sounds like your story, take a second to subscribe. What the first image actually shows. The image that started all of it is the one to look at first, because a single glance explains why 30 years of anticipation broke open the moment it appeared. At first glance, it looks like a dense scattering of stars on a black background, the deep space picture you have seen 100 times before. Then you learn what you're actually looking at, and the scale of it rearranges something in your head, because almost none of those points of light are stars at all. They are galaxies, roughly 10 million of them packed into a single frame, and each one is a city of hundreds of billions of stars in its own right. That number is hard to hold in your head, and the way the image was made is just as staggering. This is the Virgo Cluster composite, and it was not captured in a single click. It was built by taking more than 1,100 separate exposures and carefully layering them together into one picture made of about 3 trillion pixels. And when you look closely, the sameness breaks apart into astonishing variety, because these galaxies are not all doing the same thing. Some of them are in the middle of crashing into one another. In one corner sit galaxies caught mid-collision, their spiral arms still stretched and tangled together as they merge into something new. Elsewhere, 2 bright blue spiral galaxies sit side by side, and scattered across the background are swarms of small orange and red galaxies. And that color is actually a clue to distance, because the redness comes from their light being stretched out over billions of years as it crosses an expanding universe before finally reaching the camera. In other words, the further away a galaxy is, the redder it tends to look. So a single image like this holds galaxies at a whole range of distances at once. That range is bigger than it first appears. The cluster the image is named for is only a small part of what you see. Of those 10 million galaxies, just a few thousand are actually bound together by gravity into the Virgo cluster itself. And the light from those left them around 55 million years ago, long before it arrived here to be photographed. And here is the part that resets the scale one more time. Everything described so far comes from a tiny piece cut out of the corner of the full image, just a small crop of the whole thing. The complete picture covers an area of sky about 70 times the size of the full moon, and it is so large that no ordinary screen can display all of it in full detail at once. So if this were only a beautiful photograph, it would still be remarkable. Just one more gorgeous space image to scroll past. But it is not that. It is a working scientific record of millions of galaxies measured in a single exposure, and that is a fundamentally different thing. It changes what astronomers can even attempt to do. And to understand why, it helps to see the second image released that same day, because it shows this telescope doing something completely different. A look inside our own galaxy. The observatory did not release just one image that day. It released a second one, and it was almost the opposite of the first. The Virgo composite looked far out into the distant universe. This one turned the telescope around to look inward at our own galaxy. and at the exact places where new stars are being made right now. To see what that means, look at what the picture shows. It captures two glowing clouds of gas and dust called the Trifid and Lagoon nebulae. A nebula is simply a giant cloud of gas and dust floating in space. And these two are not distant galaxies at all, but nurseries inside our own Milky Way, places where gravity is slowly pulling material together until it collapses and ignites into brand new stars. They sit in the direction of Sagittarius, one of the constellations we see from Earth, a little over 4,000 light-years away, which in cosmic terms is practically next door. And like the first image, this one was not a single snapshot either. It was built from 678 separate exposures, layered together over about 7 hours of observing. That patience is what unlocks the detail, because stacking that many images together slowly pulls faint features out of the dark, the soft folds of glowing gas and the black lanes of dust winding through them, detail that a single quick photo would lose completely. And the contrast between the two images is the whole point. One looks billions of light-years out into deep space, at galaxies as they were long before Earth even existed. The other looks close to home, at the raw material our own galaxy is using to build its next generation of stars. Both came from the same instrument, on the same day, using the same enormous view of the sky. Which raises the obvious question: what machine can look all the way across the universe and deep into our own galaxy, capture both in this much detail, and do it while it is technically still just being tested? To answer that, you have to look at the telescope itself and at the camera bolted into the heart of it, the machine that made it possible. The instrument behind both those images is the Vera C Rubin Observatory itself, which sits on a mountaintop called Cerro Pachon, high in the dry, dark skies of northern Chile. At its core is a telescope called the Simonyi Survey Telescope, and its main mirror is 8.5 meters across. But size alone is not what makes it special, because plenty of big telescopes exist. What sets this one apart is that it was designed to see an enormous slice of sky sharply, all at once, using an unusual arrangement of 3 mirrors working together to keep the whole wide view crisp rather than just the center. That main mirror is a story in itself. It was made from a single piece of glass, and shaping and polishing it took about 7 years of painstaking work until it was finally judged essentially perfect. A mirror that big and that precise is one of the hardest things to build in all of astronomy. But as impressive as it is only half of what makes the telescope work. The other half is the camera, and this is the part that genuinely breaks the scale of anything that came before. It is called the LSST Camera, named for the legacy survey of space and time, the great 10-year sky survey it was built to carry out. It takes pictures at 3,200 megapixels, and it is the largest digital camera ever built for astronomy. It is not a camera you could hold. It is roughly the size of a small car and weighs around 3 tons. The numbers behind that resolution are almost hard to picture, so here is one way to feel it. To display just one image from this camera at full detail, you would need about 400 ultra-high-definition televisions arranged together, a wall of screens roughly the size of a basketball court. And that scale continues down into the smallest parts of it. Inside the camera, the light is caught by a grid of 189 separate sensors, and those sensors are chilled to about -100 degrees Celsius. That deep cold matters for a simple reason. Warm electronics create a faint background hum of their own, a visual static, and that static can drown out the faintest, most distant objects the telescope is straining to see. So cooling the sensors keeps that noise down and lets the faint things show through. With every single exposure, the camera captures a patch of sky about 45 times the size of the full moon. But a camera this enormous and this sensitive was not built to take one beautiful picture and then stop. It was built to photograph the entire sky and then come back and do it night after night. And that repetition is where the Rubin Observatory turns from a camera into something closer to a discovery machine. The discovery engine. The real breakthrough is not any single picture. It is what happens when you take the same picture of the same patch of sky over and over, and then compare each new image against the last one. Once you can line up last night's sky against tonight's, anything that has changed in between suddenly stands out. A point of light that was not there before, or one that has faded, or one that has shifted position, jumps straight off the frame. And that is exactly what Rubin is built to do across the entire sky. What makes that possible is speed, and the speed involved is genuinely hard to believe. As the telescope works, it processes each fresh image and flags anything that has changed in under 60 seconds. And the number of changes it expects to catch is staggering. The observatory is built to send out up to about 10 million alerts every single night. And each alert is simply a pointer telling astronomers exactly where to look, whether it is an exploding star, a feeding black hole, or an asteroid slipping across the view. Keeping up with that flood means handling more data than astronomy has ever dealt with. Every night, the telescope produces tens of terabytes of information, and a terabyte is already a huge amount, roughly the space it would take to store hundreds of hours of high-definition video. By the time the survey is finished, it will have gathered more data than has effectively ever been written down in any language in the whole of human history, which is why an entire computer system had to be built just to catch it all and pass it to scientists fast enough to be useful. And this is the part that changes what astronomy even is. For most of its history, astronomy has worked in snapshots, single deep pictures of a sky that was treated as fixed and unchanging. But the sky is not fixed at all. It is constantly in motion, with stars exploding, rocks racing past, and distant galaxies flickering as the black holes at their hearts feed on matter. Rubin is the first telescope built to watch all of that unfold live, across the whole sky at once, capturing the universe in motion instead of freezing it in a single still frame. A machine like that does not appear out of nowhere, though. Before Rubin could photograph a single galaxy, it took nearly 30 years of work to build. And that long road is a story worth telling on its own. Before we get into how this thing was built, take a second to subscribe. The 30-year road to first light. It is easy to look at those first images and think of them as a beginning. In truth, they were the finish line of a race that had been running for almost 3 decades. The idea for Rubin was first proposed around the year 2001. Back when the whole thing existed only as an ambitious pitch on paper. And an idea on paper is a very long way from a working telescope on a Chilean mountaintop, which is exactly why it took so long to get there. Construction did not formally begin until 2014, and even then, the hardest pieces each took years on their own. The main mirror alone, that single flawless disc of glass, ate up about 7 years of shaping and polishing. And the mirror was only one part of it. The car-sized camera was a separate epic in itself, built and tested over years at a national laboratory in the United States before it ever traveled south. And then, partway through, the world stopped. The COVID-19 pandemic shut down work on the summit and stalled progress that had already taken years to reach. Even setting the delays aside, this was never the work of a handful of people. It took hundreds of scientists, engineers, and staff spread across many countries, along with decades of funding and problem solving, all pointed at the same distant goal of getting one telescope to finally open its eyes. Which is why, when the first images finally arrived in June of 2025, the reaction was so much bigger than admiration for a few pretty pictures. It was the release of 30 years of held breath. Many of the people involved had waited most of their careers for this exact moment, and when it came, the world celebrated it together. Watch parties were held on 6 continents at once, a global moment shared by everyone who had spent years helping bring this telescope to life. That is what the first light of this telescope truly represented. Not just a photograph, but the payoff of an entire generation of work. And there is one more thing worth knowing before we move on, because the name on the building is not a coincidence. This telescope carries the name of a real person, an astronomer whose own discoveries are woven directly into what Rubin was built to chase. The woman it's named for, the telescope, is named for Vera Rubin, an American astronomer who ranks among the most important figures the field has ever produced. And the reason her name sits on this particular observatory is not honorary decoration. It is a direct nod to the exact mystery this telescope was built to chase. To see why, you have to look at what she discovered. Her great work came from studying something that sounds almost too simple to matter: the way galaxies spin. Picture a galaxy as a giant spinning disk of stars. Rubin measured how fast the outer edges of these disks were turning, and the numbers made no sense. The galaxies were spinning so fast that they should have torn themselves apart and scattered their stars into space. The only thing that stops a spinning galaxy from flying apart is gravity. And gravity comes from mass, from stuff. But there simply were not enough stars and gas in these galaxies to produce that much gravity. So something else had to be there, something invisible, quietly adding the extra pull needed to hold everything together. That invisible something is what we now call dark matter, and Rubin's measurements were some of the first strong evidence that it truly exists. It was a quiet revolution, because it meant that everything we can actually see in the universe, every star and galaxy, is only a small fraction of what is really out there. And that is the thread that ties her name to this telescope. Dark matter, together with a second mystery called dark energy, is thought to make up roughly 95% of the entire universe, and we still cannot see either one directly. The Rubin Observatory was built in large part to hunt exactly that, by mapping billions of galaxies to trace the pull of the invisible mass Vera Rubin first pointed to. In other words, the telescope does not just carry her name, it carries on her work. And it began delivering on that promise almost immediately, before the real mission had even started, in a way that caught even the scientists off guard. What it found in mere hours is the detail that best captures what this telescope is. Everything you have seen so far, the 10 million galaxies, the glowing nebulae, all of it came from only about 10 hours of test observations. This was not even the real mission yet. The survey had not started. Scientists were still checking the machine over, making sure everything worked. And in that short window of testing, Rubin quietly made a discovery that would be a headline for almost any other telescope. In those roughly 10 hours, it spotted 2,104 asteroids that no one had ever seen before. Brand new rocks in our own solar system, catalogued for the first time, including 7 that pass relatively close to Earth, none of which pose any danger to us. To feel how absurd that number is, think about how slowly this work normally goes. In a typical year, every other telescope in the world put together, on the ground and in space, finds only about 20,000 new asteroids. That is the total for an entire year, from every other instrument combined. Rubin found more than 2,000 in a single testing session, and over its first 2 years, it is expected to find millions. That is not a small improvement on the old way of doing things. It is a completely different scale, a machine that can catalog the moving pieces of the solar system faster than anything ever built, which also makes it one of our best tools for spotting anything that might one day be heading toward us. And the striking part is that asteroids are almost a side effect. Finding them is a bonus that falls out of the telescope's real job, which is far bigger and stretches out across the next 10 years. The 10-year mission. And now that Rubin has finally opened its eyes, here is what the next decade actually looks like. The real job is called the Legacy Survey of Space and Time, and the plan behind it is almost absurdly ambitious. The telescope will scan the entire southern sky over and over, capturing the whole thing every few nights, taking a fresh image roughly every 40 seconds, and it will keep doing that, night after night, for 10 straight years. Stitched together, all of that becomes something no one has ever had before. A time-lapse movie of the universe, which the team behind it has called the greatest cosmic movie ever made. By the time it is finished, it is expected to have cataloged around 20 billion galaxies and 17 billion stars. A map of the sky so complete, it makes everything astronomy has assembled up to now look small. And this is where that number from the very beginning finally makes sense. Remember the first image, the one holding 10 million galaxies, the one so large no screen could show it. That image, overwhelming as it was, captured only about 0.05% of what this survey will eventually see. 10 million galaxies, and it is barely a rounding error. Rubin was built to capture the other 99.95% again and again, watching all of it change over time. That flood of data is aimed at some of the biggest open questions in science. It will let astronomers trace the invisible dark matter that Vera Rubin first found evidence for, and study the dark energy that is pushing the universe apart, including recent hints that this force may be slowly weakening. Closer to home, it will map our own Milky Way in fresh detail, catch rare and violent events like the collisions of dead stars that forge gold in an instant, and even join the search for a possible hidden giant planet, sometimes called Planet 9, that may be lurking in the cold outer edges of our solar system. Each one of those is a major question on its own, and Rubin will be working on all of them at once. 10 million galaxies in a single frame, and that was only 0.05% of what is coming, which means more than 99% of this map is still out there, waiting. What truly stopped astronomers cold was realizing that after nearly 30 years of building, this machine was only taking its first pictures. The greatest cosmic movie ever made is only beginning, and it will unfold night after night for the next decade. If you enjoyed this one, hit subscribe